In this video, we'll discuss an interesting way to prove statements about the natural numbers known as mathematical induction. To get things started, let's consider a little thought experiment. Suppose that on the first day of class, a mathematics professor tells the class that their grade for the semester will be determined by a pop quiz given on a day that nobody will expect. A student raised her hand and said that such a thing was impossible and explained her thinking. The professor was impressed and awarded the student an A. What was her argument? Pause the video and ponder. Think about what the argument might have been that so impressed the professor. Like many puzzles, there might be more than one answer to this question. One answer, though, is particularly interesting. Suppose that the girl argued that the quiz could not be given on the last day of class. For if the professor waited until the very last day of class for the quiz, then everyone would expect it on the second to last day of class. However, if they can all rule out the last day of class, then they can also rule out the second to last day of class, because if the professor waited all the way till 3 days left in the class, he couldn't give the quiz on the second to last day of class because then the students would expect it. They know it wouldn't be the last day, so it would have to be the second to last day. Continuing this reasoning down the line, it's impossible to give a pop quiz that nobody would expect. This brings us to a definition of the term that this video is all about, and that's mathematical induction. I'll remind you that whenever you see these little icons up in the top corner, that's an idea that is really worth remembering, and you should jot it down in your notebook. In this case, our definition is for mathematical induction, which is a method used to prove statements involving natural numbers, and it involves verifying the truth of two very important conditions. Condition 1, you must verify that the statement is true for some particular number n. And condition 2 says if the statement is true for some number n, then it follows that the statement must also be true for the next number, n plus 1. A helpful visual to have in your mind when writing an inductive proof is a set of dominoes, an infinite set of dominoes, each domino representing a different natural number or a statement about a different natural number. Condition 1 in an induction proof says, let us verify that the very first domino does indeed get knocked over. Condition 2 does not say anything about the second domino or the third or the fourth specifically. Instead, condition 2 says, let's try to verify that whenever domino k gets knocked over, domino k plus 1 also gets knocked over. And this is called the inductive step of the proof. You see, when we generalize about domino k and k plus 1 and can verify that k always knocks over k plus 1, we then are able to represent k and k plus 1 as domino 1 and domino 2, or 2 and 3, or 3 and 4, or any one that we choose. So once condition 1 and condition 2 are verified to be true, we can conclude that every single domino gets knocked over. In our first example, we're asked to prove that 1 plus 2 plus 3 and so on up to n, so the sum of the first n natural numbers, can be found using this nice shorthand formula, n times n plus 1 divided by 2. And a couple of details here. A lot of times in proof, we like to use a shorthand. This upside down A stands for all, or for every. And then n, and then this symbol here means in the set, or belonging to the set. In the set, every n in the set of, and you've seen this n before, this means natural numbers. So you can use this shorthand if you'd like, or you could just write it out fully. You save a little time by using the shorthand. So this says, prove that the sum of the first n natural numbers is equal to n times n plus 1 over 2, and that this works for every natural number. Okay, and this is why we need a mathematical proof, is we could verify that this statement is true for 1 plus 2, or 1 plus 2 plus 3, or if we had a lot of time on our hands, maybe all 1 plus 2 plus 3 all the way up to 100, like Gauss did in the story we mentioned in an earlier video. However, we could never prove that it was true by verifying case by case. And so we need something stronger, and mathematical induction is just the tool to get it done. We'll start with condition 1, which says, show that the statement is true for n equal 1. Well, when n equals 1, the left-hand side is simply 1. We don't have anything to add yet because we only have the first natural number. And the right-hand side of the equation, n times n plus 1 over 2, would be 1, multiplied by the quantity 1 plus 1, divided by 2. And you can check that that arithmetic works. 1 plus 1 is 2, divided by 2 is indeed 1. We don't need to check that the statement is true for n equals 2, or n equals 3, or n equals 4. However, I might advise that you take the time in a new induction proof to check for several initial cases. This will allow you to familiarize yourself with the problem and really understand what it is that you're trying to prove. So next we'll take a look at condition 2. Condition 2 challenges us to show that if the statement is true for some number n, then it must be true for the next number n plus 1. Proving condition 2 is a little more work than proving condition 1. And in fact, understanding condition 2 on its own is a little more work as well. So the first thing to know is that we're trying to verify an if-then statement. We need to have a quick conversation about if-then statements, since if-then statements are such a big part of induction proofs. Consider the statement on the backboard here. If it is Friday, then I'm wearing socks and sandals. I claim that this is true. Every single Friday, I'm going to put on socks and sandals before I go to work. Even if I'm not going to work, that's going to be my footwear of choice. Suppose you wanted to verify this statement, and you're like, hey, Mr. Hawkins, what's on your feet? What does that tell you about the truth of this statement? I'm wearing sandals, wearing socks. Does that mean it's Friday? What do you think? In fact, the fact that I have socks and sandals on right now really has nothing to do with this statement. It can't prove it true, can't prove it false, because this statement right here is all based on the if part. If it is Friday, this is going to happen. Right? Today's actually Tuesday. I'm just wearing socks and sandals because I feel like it on Tuesday. This statement doesn't say anything about Tuesdays. It only says things about the if part. If it's Friday, this statement would be false if you knew in fact that it was Friday and you look down at my feet and you're like, why are you wearing sneakers? What's going on there? That would make it a false statement when the if part's true and the then part is actually incorrect. That's very, very important because when we talk about an induction proof, we say if this is true for some number n, then let's prove it true for the next number in line, the n plus 1. And in an induction proof, that's a reasonable assumption to make if it's true for some number n. Because if you think back to condition 1, we showed that it was in fact true for n equals 1. So saying then, after we know it is true for some numbers, to say if it's true for some, then let's go and do this next thing, that's a good way to prove something in a valid way. So let's get back to the problem about showing that the sum of the first n natural numbers was equal to n times n plus 1. For the if part of the statement, we make the assumption. We say, let's assume that it is true that 1 plus 2 plus 3 plus n is equal to n times n plus 1 over 2. And this is very important here. I'm going to use a different symbol than I used before. If you recall, in the initial part of the statement, I used the symbol of an upside down A, and that upside down A represented for all. The symbol that I've drawn here looks sort of like a backwards E, and this means not for all, but instead for some. So this says, let's assume that the statement is true for some number n, and for some in math means at least 1. And what I'd like to show now is that the statement also works for the next number in line. So the show part would look like this, 1 plus 2 plus 3, okay, plus n, but then I need to also add the next number in line, and that would be n plus 1, okay? And what would it mean for the right-hand side to work out? Well, now instead of n, I would have n plus 1. Instead of n plus 1, I'd have n plus 1 plus 1, or n plus 2. Okay, so this is exactly what I need to show right here, that the sum of the first n plus 1 natural numbers also works out according to the formula. So here's the actual proof, or the algebraic part that verifies the induction. I verify the truth of the show step. And this is pretty easy to do. What I'm going to do here is I'm going to substitute 1 plus 2 plus 3 plus n with what I know to be equivalent to it from my assumption here. So I'm going to swap the green out for the green, right? So I'll have n times n plus 1 over 2 plus n plus 1. And I want to show that this is equal to n plus 1, n plus 2 over 2. And when I say that I want to show it, what I'm just going to indicate here is I'm going to put a question mark above the equal sign. I want to verify that that equality is in fact true. So you'll see all I'll do is I'll manipulate the left side of the equal sign until it's clear that the two are equivalent. Let's see. I have a fraction to add to n plus 1, so maybe a common denominator is in order. So let's do n times n plus 1 over 2 plus 2, n plus 1 over 2. I want to show that that is indeed equal to n plus 1, n plus 2 over 2. All right, now that I have a common denominator, I can add those numerators together and write them under the same denominator, n times n plus 1 plus 2 times n plus 1. Okay, and then at this stage, you're actually very close to being done the proof. Okay, there's a couple different directions that you can go. One direction that you could go is you could distribute the n here and the 2 through the parentheses. And then you'd have a quadratic that you could factor. And hopefully it factors just right to see that the proof is in fact done. Another strategy that you'll see is often very useful is I'll look for common factors. And I notice that in my numerator here, n plus 1 is indeed a common factor in the numerator. So I'll factor that out rather than distributing. If I factor out an n plus 1 on the left-hand side, I'm left with an n right here, and then a plus 2 right there. So I have n plus 1 times n plus 2. Oh, look, and over 2, and that is exactly what I see on the right-hand side. That was my goal all along. All right, and then the only thing left to do is to write a nice conclusion. And what I mean by that is I've shown that condition 1 is true. I've shown that condition 2 is true. And now I can say, therefore, the original statement, and the original statement was 1 plus 2 plus n equals n times n plus 1 over 2. That's the original statement that I'm referring to, is true. Here comes the upside down A again, for every natural number, every n in the set of natural numbers. And there's our first induction proof. In our second example, we're asked to prove that the sum of the first n odd numbers is always equal to the nth perfect square, that statement is true for every natural number. The way we write that mathematically is right here. Prove that 1 plus 3 plus 5 and so on, plus 2n minus 1, since 2n minus 1 will always describe an odd number, is equal to n squared for every n in the set of natural numbers. Now, before we get into the inductive proof on this, I'd like you to consider a much simpler proof, a proof without words, as it's called. This image right here in front of you should convince you that the sum of the first n odd numbers is always equal to the nth perfect square. Can you see why? Pause the video for a second and think about it. The way I think about this proof without words is I see my first odd number in that square, and I see my second odd number 3 in this little backward L shape right here. And I see that 1 plus 3 together make 4, and of course 4 is 2 squared. I added 2 odd numbers, and I got 2 squared. Meanwhile, if I were to add another odd number, the next one would be 5, and that's that L shape there. And 1 plus 3 plus 5, of course, makes another square, and that's 9. The problem with this proof without words is, well, I only see that this works up to 11. 1 plus 3 plus 5 plus 9 plus 11 is the sum of the first 6 odd numbers, and thus it's equal to 36, or 6 squared. It hasn't convinced me, and that's the point of a proof. A proof should convince you beyond a shadow of a doubt that this statement is always true, that there's not a certain odd number that I could add on in which this all falls apart. And so we turn to induction. And an induction proof must always begin with condition 1. Condition 1 states that we must show that the statement is true for n equals 1. So I look at the left side of the equal sign. When n is 1, I only have a 1, not even a 1 plus 3 yet, because that would be n equals 2. On the right-hand side, I've got a 1 squared, and pretty obvious that 1 is equal to 1 squared. So I move on to condition 2. I'll remind you that condition 2 says to show that if the statement is true for some number n, then it must be true for n plus 1. We have our if-then statement. And remember, the if part is what we're allowed to assume. We're going to assume that the statement is true for some number n. Oftentimes, when you write the assumption, 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared, students will kind of hold up for a second there. They'll get a little unsure whether that's a valid thing to say, because that assumption looks a whole lot like what we're trying to prove. However, you'll notice that in my assume statement, I used a backwards E. The backwards E symbol, if you remember, this refers to for some. It's an abbreviation for some natural number, and for some in mathematics means for at least one. So this is a valid assumption to make because we know that it is true for n equals 1. Let's move on to our show step. When we write our show step, the important thing to keep in mind is that we are going to sum not just the first n odd numbers, but the first n plus 1 odd numbers. So the adjustments that I need to make for the show step is I need to add an extra term right here. This is the next odd number after 2n minus 1. Notice that I construct it by doing 2 times n plus 1 minus 1 instead of 2 times n minus 1. I adjust the right-hand side as well. Instead of the nth square, I'll be at the n plus first square. Constructing an correct show step is an important part before you begin your proof. To begin your proof, recognize that you want to show that this equation here is valid. The show step is indeed valid. Note that I made a minor adjustment to the very last term of the show step. Instead of 2 times the quantity n plus 1 minus 1, I just simplified that to 2n plus 1. Makes things a bit easier. Okay, now the first step in the proof would be to take out the sum of the first n odd numbers, which by my assumption is equivalent to n squared. So I'll substitute green for green. And now I have a much simpler equation to try to verify. N squared plus 2n plus 1 equal to the quantity n plus 1 squared. That's not so bad at all. To verify that this equation is true, all that needs to be done is factor the left-hand side. And of course, it factors n plus 1 times n plus 1, which is n plus 1 squared. And now all you got to do is write a nice conclusion. The conclusion can look like, therefore, the statement. By the statement, what I'm referring to is the sum of the first n odd numbers. This statement is true for every n in the set of natural numbers. Let's look at another example. In this example, we're asked to show that the sum of the first n squares is equal to this handy little formula over here, n times the quantity n plus 1 times 2n plus 1 all over 6. Now, this is a new idea, summing squares. And in fact, we have some more information coming about exactly what this all means. But first, let's prove its truth using induction. We'll start with condition 1. And as always, condition 1 says, let's show the statement's true for n equals 1. And so I check that 1 squared, which is just 1, is equal to 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. This is just an exercise in arithmetic, right? I'm just plugging 1 into the formula I referenced earlier. And I get 1 times 2 times 3 over 6. And yeah, that checks out. 1 equals 1. So condition 1's met. Normally, you can move on to condition 2. However, like I said, this summing squares thing is a bit new and unusual, and until we get into properties of series, we won't quite see what it means. So let's check and show that the statement is true for n equals 2. It's not necessary to do this. However, checking that the formula holds for a few basic cases is a good way to better understand what's going on here. So this time I'm going to check not just that 2 squared, but 1 squared plus 2 squared, because the left side is a sum, is equal to 2 times 2 plus 1 times 2 times 2 plus 1 all over 6. Another exercise in arithmetic. And 1 squared plus 2 squared, well, that's 5. And on the right-hand side, I've got 2 times 3 times 5, which is 30. And, well, 30 divided by 6 is also 5. So it checks out. We see that this formula is working for 1 and for 2. And we can continue in this way, and we can check that it's true for n equals 3, right? The point of an induction proof is that checking for cases like 1 or 2 or 3 is never enough to actually prove it. That's what you need the induction proof for. Checking that it works for 1 and then going on and moving and figuring out condition 2 is enough to verify the statement. But you can check the first 17 cases, and that's not enough to verify the statement because you're not sure. Maybe it falls apart on the 18th step. What condition 2 tells us is if it's true for 1, then it's necessarily true for 2, and we don't have to check 2. And if it's true for 2, then it's necessarily true for 3. And if true for 3, then 4. That is the inductive step. That's the power of the induction proof. So let's verify condition 2. If the statement's true for some n, then it must be true for n plus 1. This produces an assumed statement. Our assumed statement will look very much like what it is we were asked to prove initially, that the sum of the first n squares is equal to n times n plus 1 times 2n plus 1 all over 6. However, there's a very, very key difference that you should make sure you include in your assume step. You don't want to write that we're going to assume that this is true for every n. Instead, we want to say for some, that backwards e, for some n in the set of natural numbers. That's a legitimate assumption because we've already shown that it works for 1, 2, and 3 in this case. Our show step looks like our assume, 1 squared plus 2 squared, not just the first n squares, but the first n plus 1 squares. So we add an extra term to our sum, and the right-hand side must be adjusted too. Instead of n, we have n plus 1. Instead of n plus 1, we have n plus 1 plus 1. And instead of 2n plus 1, well, what do you think? What should go in that last binomial? Pause the video and see if you can figure out what should go in that last binomial. Did you say it was 2n plus 2? If so, you were close, but not quite. Actually, in that last binomial, we should have 2n plus 3. And the reason for that is very important. What you want to realize is we're adjusting the formula on the right-hand side so that it works for n plus 1 instead of n. So that involves replacing an n with an n plus 1. So the first binomial is pretty simple. The second, n plus 1 is n plus 2. But in the last one, you need to be careful there because what we really need is 2 times the quantity n plus 1 plus 1. I'll write that over here in a different color so you can see why we have 2n plus 3 instead of 2n plus 1. 2 times the quantity n plus 1 plus another 1, which that simplifies when you distribute the 2 to 2n plus 3. And we put it all over 6. Okay, so let's get to the proof part, I guess the heart of the proof, to show that this show step is valid. This equation right here is a valid equation. The way to do it is to recognize that we already know how to sum the first n squares for this particular number n. And what that means is I am able to replace 1 squared all the way up to n squared with this handy little formula right here. N times n plus 1 times 2n plus 1 over 6. So I substitute that in. And then I add my n plus 1 squared. And I recopy the right-hand side. So this is now just an exercise in algebra. How are we going to show that these two sides are equivalent? There's really probably a lot of ways to do this, and some are going to be more efficient than others. I think most of them will begin with this step, where we get a common denominator on the left-hand side. There's a fraction added to n plus 1 squared, so it would be good to get n plus 1 squared over 6. So my next step would probably to be rewrite the left-hand side kind of like this. And the right-hand side stays the same. In the next step, it certainly makes sense to rewrite the left-hand side all over 6. That seems like a good idea for a number of reasons, one of which on the right-hand side, I see that that entire fraction is over 6. However, if you start to think efficiently about these problems, you might come up with another good idea of something to do on that left-hand side there. One thing that I notice is that both fractions have a factor of n plus 1. And that means I'm able to factor out an n plus 1 among those two terms. If I do, I'll write it, let's see, I will write it right here, n plus 1. And I'm going to write everything that's left inside these two brackets right here. Okay, so what's left? In my first term, I'm going to have an n multiplied by a 2n plus 1. N multiplied by a 2n plus 1. Well, that's 2n squared plus n. And then in my second fraction, second part of the fraction, I'm going to have a plus 6. Oh, but that 6 will also be multiplied by an n plus 1 because the second fraction had 2 copies of n plus 1 right there. So I'll have plus a 6 times the quantity n plus 1, or 6n plus 6. Huh, how about that? Believe it or not, we're now at the very, very last step of the induction proof. From here, I can see that I have 2n squared plus 7n plus 6 inside of these brackets. And what are you going to get when you factor 2n squared plus 7n plus 6? Well, you'll get n plus 2 times 2n plus 3. And thus, we can write our conclusion. Therefore, the statement, meaning the sum of the first n squares, is equal to n times n plus 1 times 2n plus 1 over 6, is in fact true for every natural number. Okay, I hope this video would help you understand some of the basics of induction proofs. Like most things in math, you get better at them with practice. Thanks for watching.